Here's a classic trig identity proving problem. Now, the other day in class, or actually often in class, I tell my students not to anticipate what might happen if they try something, that they should just try it. And that's a perfect example of what I did in class with this particular identity. I started proving it, and I got to a point where I started just anticipating what might happen, and I couldn't finish it. Well, number one, time ran out in class, but number two, I really was looking at it and thinking, I don't know what to do. If I had just tried what I thought I should do, I would have done it right. So let's see. Let's try this one again, and I think I can get it this time. So again, when you prove any identity, you start with one side and you end with another. You don't mess around with both sides. It's just not, it doesn't work. You get confused. However, if I start with this side, this is my proof. I'm going to start with the left side. Cosine of x plus y times cosine of x minus y. And using the identities, the sum of two angles identities, I see that the cosine of x plus y is going to be the cosine x cosine y. Minus sine x sine y. And that's going to be multiplied by, now I'm going to run out of room here, so this is going to be multiplied together, cosine of x minus y. So that's cosine x cosine y plus sine x sine y. Now again, this is a product of two binomials, or two terms. So I have one term, two terms, three terms, four terms, and I'm just going to FOIL, that old-fashioned foiling kind of thing. So I'm going to multiply the first two terms together, and I get cosine squared x, cosine squared y, FO, the outer terms, so I get plus cosine x sine x, cosine y sine y. And then I multiply the inner terms, minus cosine x sine x, cosine y sine y. And then the last terms, minus sine squared x sine squared y. Okay, now that's not too bad. Just take it slow, and it's pretty straightforward. So I notice right away that this whole term matches this whole term, so they go away. So this is equal to cosine squared x, cosine squared y, minus sine squared x, sine squared y. Now again, I'm going to look back at what I... That's my dog barking, sorry. I'm going to look back at what I want, and I notice that I don't want this, and I don't want this. And there's no, it's not like I can factor anything out because all of the angles are different. And so, and there's no Pythagorean identity laying around. So what I'm going to do is replace, just try something. Replace this with 1 minus sine squared y. Because that can maybe do something with this guy over here. I'm not sure, but let's just see what happens. So I have cosine squared x minus cosine squared x sine squared y minus sine squared x sine squared y. Well, I have my cosine squared all by itself. Now then what I'm going to do, again, this is the one I don't want. I'm going to do the same thing with this guy. Because I see that I'm moving along. I want this guy. I just have to somehow mess around with these, and I'm going to try something. So cosine squared x, that stays the same. This guy stays the same. And so sine squared now is going to be 1 minus cosine squared x. Sine squared y. You got to keep a track of the x's and y's here. And that leaves me with cosine squared x minus cosine squared x sine squared y minus, okay, now what I'm going to do is do this multiplication in the parentheses. So sine squared y times 1 and sine squared y times negative cosine squared x. So that's going to be minus cosine squared x sine squared y. And I think it's going to work out. So cosine squared x, again, I'm going to take it slow here, and some of you may see where this is going, but don't worry about it. I'm going to distribute the negative, so I make sure I don't make any mistakes. And I notice that this term and this term are the same. So that's 0, and I'm left with cosine squared x minus sine squared y, which is exactly what I'm supposed to end up with. Bing. So thus, I am finished with the proof. Either one of these, if I write it right, QED.